we're going to look into what is machine code. Now, in a previous lesson, we did cover a little bit of this, and also we covered some trace of how to represent the machine code and the assembler code as well. Okay, so now machine code is the CPU in your computer will only process binary data. So this will include the instruction programs. So as discussed before, every CPU has a specific set of instructions and uses somewhat different language. So these are the instructions that you are used to. Okay, so you're used to your instructions with a title, a blurb explaining things, pictures representing things, and a clear set of steps. Now, this is a set of instructions that your computer and the CPU uses, that they are used to, that they understand. So, now binary, as you know, is a non-human friendly format. So, and those will know how to decode the instructions and how to interpret it. So you understand how to decode binary and put it into denary, which is a set of numbers that you understand. You understand two's complement, you understand ASCII code. So you understand all these interpretations of the machine. So there is some form of communication. So to improve this, obviously we use the hexadecimal system. So as you can see, binary numbers, as you know and have experienced, are just a bunch of ones and zeros. Now, the problem is with ones and zeros, they can be misinterpreted and they're prone to error. And also they'll be pretty time consuming to decode and understand. So as humans, we use this because, as you know, the machine doesn't use hexadecimals. Hexadecimals are simply for humans to interpret. And also we can interpret denary. So which you can see is this binary would represent this in hexadecimal and this may represent it in denary. So this is how we interpret and understand. Now the CPU is essentially a machine because it is the brain of the computer and it completes all the calculations. So it's kind of as if we have a machine inside a machine. A bit like your washing machine at home is basically a computer. It has a set of programs that perform instructions in a sequence. But we don't look at our washing machine and say it's a computer. But inside your washing machine is a motherboard with a CPU. So in fact, there's a machine in a machine. Now, the instructions for this are called machine code. So each CPU type will use different binary numbers to represent particular sets of instructions. So the machine code written for one type of CPU will not run on another type of CPU. So, because one CPU is different to another. So in some ways, it's a bit like different parts of the world speak different languages. So it will have to be rewritten prior to taking place. Now, the machine code, okay, does not recognize English or any other language spoken by a human. So as discussed before, so you can see by the pictorial representations here, you've got your high level languages, which is a language that would be closer to English, for example, JavaScript and Python. Then you've got your assembly languages, then you've got your machine codes. So as you can see, as the levels go down, they are further and further away from the English language. So the language it recognizes is the machine code. So the CPU will recognize the machine code. So when a program is running, an instruction is fetched from the memory, this will be in binary format. But the different processors have different instruction sets. So in some cases, the processors may have the same instruction, but the code structure may be different. So an example of a component for an individual machine code instruction would be the total number of bits and bytes for the whole instruction, the numbers of bits that state the operation codes, this would be the opcodes, it's abbreviated as opcode, and the number of operands that are defined in the remaining bits. So the opcode occupies the most or least significant bits. Okay, the opcode is the part of the machine code, the operation, remember it's the operation code. It's the part of the machine code, the instruction that defies the operation to be performed. Then the operand is the term used to describe any object that is capable of being manipulated. So for example, we've got 1 plus 2, and the 1s and 2s, the operands, the plus symbol is the operator. So now, the number of bits needed for the opcode depends on the number of different opcodes the machine is set for the processor. So it's structured with a few bits stating the operation. So this is what it looks like here. So if we was to break this down, so the operation will have 4 bits, 2 bits in the address mode, the registering address is 2 bits, then the operand is 16 bits. Okay, so if we take a look at this, here basically is split into 4 bits, so this occupies the most significant. So basically this is all part of the opcode. Okay, all of it is part of the opcode. Then we split it down, okay, into basically different bits. Then for the operand, we need to allocate 16 bits because it can be used to directly address to the memory. Now moving on to assembly language. So this is the low-level programming language used, programming designed for specific processor types. So the programmer may wish to write a program where the actions are taken by the processor and directly controlled. However, writing a program in machine code to go into assembly language is going to be very, very time consuming and prone to errors. So the assembly language that it goes into would provide us with a solution to prevent that. So what it does is, the principle of the assembly language is for every machine code instruction, there's a corresponding assembly language instruction. Because as we know, as we said, every processor works differently. So this is in fact some kind of translator. The corresponding assembly language consists of basically symbolic abbreviations for the opcode, and you have seen forms of assembly language in the previous lesson, and a character representation of the operand. So when a program has been written in assembly language, it then is translated into machine code, which is your 1s and 0s, before it can be executed to the processor. Because if you remember from last lesson, the abbreviations will not be understood. Okay, so it needs to be translated into the assembly language, which is effectively probably loads of 1s and 0s before it could go into the processor. So in fact, the assembler has to be used to allow the programmer to include some special features such as comments, symbolic identifiers for constants, labels for addresses, macros, subroutines, and directives. And system calls as well. So these first 3, the purpose of them is to directly assist the programmer. So they have very little to do with the machine and its process. So the macros, these are subroutines, they're instructions. So what happens is the macros get created, so the same instruction doesn't have to be created and executed time and time and time again. So the macro will be saved so it can actually be taken and used again and used again and used again. Because the whole point of the macro is that it is part of the subroutine that has to take place at time and time again. Then your directives and your system calls. These are instructions that the assembler knows how it should construct the final executable machine code. So this will involve directing the use of memory, defining files and procedures. There's no binary conversion needed for this. So now we need to look on to the last part, which is the 2-pass assembler. So now the assembler is a program for converting instructions written in a low-level assembly code to be relocatable machine code and generating along the information for the loader. So it generates instructions by evaluating mnemonics, which are symbols that remember you saw last lesson, in our operation field, and find the value of the symbol and literals to produce machine code. Now, if assembler does all this work in one scan, it's called a single pass. Otherwise, it will tend to be called a multiple pass assembler. So I've got this one, Geek for Geeks. So the 2-pass assembler is not necessarily an essential requirement, because you can use a single pass assembler, which obviously will work much quicker. An assembly language program contains features to help the programmer and others that are used to inform the assembler program. So the passes are, pass 1 will be definitive symbols and literals to remember them on a symbol table, keep track of the location counter, and process any pseudocode operations. And then this will generate the object code by converting the symbolic operation code into respective numeric opcode. And then it generates the data for literals to look for other symbols. Now, thank you for watching. Please subscribe, like my videos. Teachers, visit my shop on TESS and follow me on Twitter. Thank you very much.